Welcome all. Good morning, afternoon, evening, depending on which part of world and time you connected from. In this session, we're gonna talk about how we can leverage Cosmos DB for storing time series data in an IoT application. My name is Ashish Balgat. I've total 15 years of industry experience. I currently play cloud solution architect role at ThoughtWorks India. I'm a certified Azure solution architect. I'm passionate about distributed systems, serverless, and building cloud native application. Other than work, you're gonna find me playing one or the other sport just to keep myself fit and motivated. This is the agenda which we're gonna try to cover today. We'll talk about what is time series data. Uh, we'll briefly talk about Cosmos DB. I would just say introduction piece, and then we'll look at the IoT reference architecture. It will be followed up with time series data store requirements, Cosmos DB features, how we're going to leverage Cosmos DB to store this time series data. We'll have a demo which where we'll look at end-to-end IoT pipeline, how the data is been sent by the simulator and how it's getting stored in Cosmos DB, the time series data, and then few key takeaways. Let's get started. What is time series data? Um, Time series data are always associated with time and they are ordered chronologically. A sequence of data points typically consists of successive measurements made from the same source over a time interval. Time series data are kind of events, message which are tracked, monitored, and they are aggregated over time. This could be sensor metrics, application performance monitoring, IoT sensor data, clickstream logs, or stock prices as well. You can typically call um, data collected over time. One of the important thing is there's no update and this data is continuously getting added at the defined sample frequency. When we plot this time series data on the graph, one of the axis will always be time, and the rest of the y-axis or the other axis will be actual metric. Take an example of stock trade and quotes. This is one of the time series data. The stock prices are always associated with time, and generally you range query. You put a range query last 5 years of stock price. So take an example of I've plotted here last 5 years of Microsoft stock, and you have seen each data point is associated with time. The y-axis has the stock metric value, and the x-axis has the time over the different period how the stock has performed. IoT sensor data. This is another example of time series data. In the above, and in this graph, you have seen temperature and humidity sensor associated to a device that are continuously monitored in a real-time fashion. And the y-axis again here is the humidity and the temperature metric, and the x-axis is the time. This is not a time series data. This is social graph. You have users, apps, and various things such as food. Important thing about this data is relationship within the graph vertexes. User A is friend of user B, user A cook vegetable, user A listens to Spotify. We are not worried how the graph relationship change over time. So in case if you have any data that does not evolve over time, or you don't care about time, probably that's not the right candidate for the time series data. Let's jump onto the Cosmos DB introduction here. Um, this is like a house diagram, and it's kind of laying a foundation at the bottom layer, and on top of that you're going to have these multiple layers. Cosmos DB is a distributed database, which means it runs on cluster of machine as opposed to a single machine. Cosmos DB scales at two dimension. It shards and also partition the database, and this allows ability to ingest large amount of data at a very high rate. Cosmos DB provides ability to replicate the data locally as well as globally, and that enables redundancy. We can even go ahead and set up a multi-master environment where data is continuously synced across two geographical locations. NoSQL database are usually divided in four families. Um, its key value, column family, document DB, and the graph. And more importantly, Cosmos DB supports all of those four. We have another layer on top of it, that's an interface layer. So Gremlin API is used to interface with graph database model. For more document DB, we have SQL API, that's native API, and the Mongo API. Column family, we have Cassandra API, and key value, we have a table API. Having said that, we can always target existing Mongo and Cassandra application to seamlessly migrate in Azure Cosmos DB. One last thing, Cosmos DB is fully managed service and provides SLA with, I would say, with 5 nines, which is pretty high compared to other data store options. So far, we have covered time series DB. We have looked at Cosmos DB briefly introduction. Now we'll briefly understand how the IoT reference architecture use looks like. This reference architecture uses Azure platform as a service components, and this is majorly divided into three components, I would say. On the left side, you see devices and how they publish sensor data to the cloud gateway. On the middle, you have data ingestion and the storage layer. And on the right side, you have data visualization, reporting, and the monitoring tool. We'll see in detail each of these. On the left side, devices. Azure IoT supports a large range of devices, starting from microcontrollers, which runs Azure Autos, or to a development boards like BeagleBone or Raspberry Pi. They support multiple communication protocols between the device and the cloud IoT gateway. It can go over HTTP, MQTT, or an AMQP WebSocket as well. Azure IoT Edge basically allows you to run cloud analytics and custom business logic on the device gateway side. You could run some device aggregation uh, logic at the edge side as well. Let's talk about one of the IoT industrial IoT client which I've worked in the past. They had multiple manufacturing plant located across the globe. They have installed sensors like temperature, humidity, pressure in their plants. As said earlier, these are the factories or the plants all over the globe. Each plant is connected to the nearest IoT hub, and the device gateway which is installed in the plant sends telemetry data at the defined interval, which is 5 second, as low as 5 second, or it can go to 5 minutes or an hour of data sampling frequency to the cloud gateway. This is the cloud gateway and the data ingestion layer. Azure IoT Hub is a cloud gateway service that can securely connect and manage devices. It provides high data ingestion capability. IoT Hub, um, think it of similar to Apache Kafka in open source world. Azure device provisioning enables zero touch, just in time provisioning that helps to register large number of devices in secure and scalable manner. At a high level, there are three ways you can process data: hot path, warm path, and the cold path. The hot path analyzes the data in the real time as it arrives. In the hot path, telemetry must be processed at very low latency. The data is pulled out of from IoT Hub. The Azure function, data ingestion function, gets triggered. It does the minor transformation and stores that into the Cosmos DB. We should leverage Cosmos DB change feed feature. We're gonna see that in future slides as well, to run some rules engine to identify any anomaly in the real-time fashion and trigger an alarm or an alert accordingly. The focus of the session gonna be on warm path, the hot path, but we'll briefly touch base on warm and cold path as well. The warm path analyze the data at the longer delay for more detailed processing. Consider using ADX, Azure Data Explorer, and Azure Time Series Insight for analyzing these large volumes of data. On the cold path side, it's predominantly used during batch processing, which gonna run hourly or probably a daily basis. The cold path typically operates over large volume of data, which may be stored in Azure Data Lake Gen 2, and that is I mean, the result not needs to be very timely as compared to hot or warm path, and hence we could use Azure Databricks, Azure Machine Learning to analyze this cold data. This is the visualization layer in the reference architecture. You can use the insights gathered out of the raw data for your environment. This is the business visualization layer where you can also build real-time monitoring dashboard apps for continuously monitoring the telemetry data and the alarms. The alarms can be notified via text, email, or the push notification. We're going to have mobile and web apps as well. So in nutshell, we have seen a typical IoT reference architecture, which consists of three layers, such as devices on the left side, data ingestion, we have hot path, warm path, and the cold path. And then we have the data reporting, data visualization layer on the right side. The session going to be focused on how can we build the hot path pipeline, and how can we leverage Cosmos DB to store that time series data, which is been pumped from the devices, IoT devices from the field. We have seen IoT reference architecture, and now we're gonna look at what are the different data entities applicable in an IoT application. Alarms, entitlement, device metadata, over the air firmware updates, and tenant management. These are the different entities, data entities which are stored in a typical IoT application. Alarms are associated to a device telemetry data uh, when certain threshold reaches. Take an example: if the temperature sensor in the manufacturing plant reports more than 150 Fahrenheit, the alarms will be raised and get notified to the respective supervisor. Alarms are captured as semi-structured data and using the JSON format, JSON document, I would just say. Similarly, we have entitlement, which is a user-based access control. The entitlement data consists of roles and permissions which are assigned to the user to perform any action. This data is again captured in a semi-structured JSON format. Similarly, we have device metadata, OTA, tenant management data, which can be easily modeled in NoSQL document. All the above data models have similar data requirements and can be stored in Cosmos DB seamlessly. But the time series data is a little different, have a different set of requirements. More importantly, in this session, we will focus on how we can model this time series data and leverage Cosmos DB's features to store this data out there. The goal, is to make Cosmos DB as one-stop solution in an IoT application data landscape. So, we talked about what time series data is all about. Now, let's talk about what are the requirements of a typical time series data store. Um, and again, we're going to take an example of IoT here, but this applies to stock trading, clickstream logs, any data which is associated to a time. One of the critical requirement is to handle scale. In an IoT scenario, we have seen, I've worked with the clients and seen 100,000 devices are connected on the field and sending data at scheduled cadence. It could be as low as 5 seconds or can go up to 5 minutes as well. We need to support high data ingestion capability with a huge volume, and this is one of the fundamental requirement of any of the time series data store. The time series data has all the necessary information, and that's the reason it has few relationship with the rest of the tables. The time series data is write heavy, and the data is continuously getting appended at the end with the newer timestamp, so that there are no updates to an existing stored data. Think of it as a write ahead log. One of the another fundamental requirement of the time series data store is retrieving this telemetry data, which is stored at very low latency. Take an example of a building BMS, building management system operator, which is continuously monitoring the HVAC, um, the lift of an entire building premises. He's real time monitoring it. So it's very critical for him to have this real time monitoring capability available out of box from this data store. Another requirement is the large range scan queries. Take an use case of if you want to fetch a telemetry data, um, energy consumption. So one of the client which I worked in the past, they they wanted to look at the energy consumption for the manufacturing plant for the last 3 months, 6 months, and a year. These are the large range scan queries, and that's another requirement. These are the top requirement for the time series data store, and we'll see how Cosmos DB can help us to achieve that. There are many Cosmos DB features, but we'll focus on these four to configure and optimize to store time series data: partitioning, auto scale request units, change feed, and time to live. Let's go one by one. Cosmos DB partitioning. Cosmos DB let you query your data with very low latency at any scale. In order to achieve this, it needs to spread your data out in shards or a different partition with some identifier, and this is your partition key. All documents which share the same partition key will end up stored and accessed from the same logical partition. Let's assume if device id is treated as a partition key, then all the telemetry data associated to that device will get stored in one logical partition. And when you query for that device, you only touch base that particular shard and not the entire table scan. There's always a limitation with each shard. There's a limitation with each logical partition, which is 20 GB for now. So if you have a device telemetry cadence at 5 seconds, we may fill that partition sooner, probably in a year, depending again on your document size. Another another better recommended approach to choose the right partition key is to append have a composite key. Have your device ID along with year or month. In that way, you have enough space to accommodate multi-year device data. We need to ensure when we query, the query is based on the partition key, um, which is part of the where clause, to get the low latency response, probably a single digit millisecond. Cosmos DB request unit. This is a unit of measurement of how much CPU and memory has been utilized to perform any Cosmos DB operation, may it be read, write, or delete. As IoT data ingestion can be at high speed and huge volume, we should configure auto scale feature at the database container level. This will just help us to automatically scale up and scale down based on the data ingestion load. You can also perform this request unit modification operation through programmatically API when you're doing batch input and output. Cosmos DB TTL and change feed. Cosmos DB change feed feature basically triggers Azure function for any change in the data store. You write a new document into a container, you delete, you update, and Azure function gets triggered behind the scene. So as soon as the telemetry data is inserted, an Azure function kicks off, and you could leverage this Azure function to run rules engine, which can detect anomaly and raise alarms notification instantly. We should leverage Cosmos DB in an hybrid way for storing this time series data. Break data into hot store and a cold store. So the hot store gonna be part of the Cosmos DB, and the cold store can be part of the commodity storage like cheap storage like Data Lake Gen 2 or the blob storage. This can be achieved by using the Cosmos DB TTL, which will basically automatically prune data from the hot store, and change feed will be leveraged to replicate data from hot store to cold store. Hot store enables low latency index query over recent telemetry, while meanwhile cold store enables low cost commodity storage for batch processing or large scanned queries. Another important point here is Cosmos DB doesn't charge you for any deletion of your document. So when you have a TTL of 1 year, uh, you're not basically charged for that, and we should leverage that functionality. Let's look at the demo, and then we can come back again on the slide deck. So what I've set it up here is I have a device simulator. I'll show that. uh, so I have created a device simulator which basically pumps huge amount of data to the cloud IoT hub gateway there. um, yeah, so it's basically, um, I've configured number of devices, and it parallelly sends pumps data, huge amount of data to the cloud IoT hub over MQTT protocol. Then we're gonna see, we have set it up IoT hub, so which will receive this simulated data and store it into the IoT hub queue. And further, we have function data ingester. This is the serverless consumption function, which will get triggered as soon as the new message gets arrived in IoT hub. This function will do some minor transformation, add some metadata, and then store it into the Cosmos DB storage as an telemetry data. So I can quickly show you that function code. So this is the data ingester function. Yeah, it basically connects to Cosmos DB. It pulls the data out of the IoT hub trigger and stores that into Cosmos DB as it is. Let's quickly look at the Cosmos DB account. Let me run the demo. You can see this in action. Let me go to the function data ingester. You have function here. This is the data ingester function. We'll look at the live logs now, and we'll hit and we'll start the simulator. So you're saying this simulator is pumping data in, I believe I've configured 5 devices, and parallel it's pushing data for each of these devices. When you go back to, you could see in the function, so the messages goes to IoT hub, the function gets triggered, and you could see the function basically further stores this data into Cosmos DB, and each of those operation consumes single digit RU here. Yeah, so this is going to happen. I think I've started batch of 10,000 messages per device there. Let's look at the Cosmos DB quickly. So this is the telemetry data database. I have a device data store. This is the container. I'll look at the settings out here. So we have this an year of TTL configured here, time to live, and more importantly, the partition key is device ID. And as I said, we always recommend to use the composite partition key as well. If you see, the data for each device is gonna be huge volume. Let's look at one of the document which data is getting stored here. Yeah, so that's basically, you have device temperature, humidity. I think these are some random values, and this is the timestamp which is getting associated to which each data point. One of the important thing of Cosmos DB is it has auto index feature, which we should use it. So tomorrow, if there's any schema change, if you add another sensor, let's add you add a pressure sensor, you don't need to, traditionally in the relational database, you need to alter table, you need to add another new column, you need to add an index for it. But in Cosmos DB, because of the auto index, it just takes care of it. Again, this is schema agnostic data store. So the version 2 of the device data will get start storing here with another pressure as a parameter sensor value with that appropriate value, and that pressure will be automatically indexed. So that's all about the demo here. Let's go back to the slide deck. Okay, let's quickly take key takeaways out of this session. uh, the four and first most, Cosmos DB does support the high data ingestion rate. It we should leverage the partitioning appropriately, and leverage the auto scale request unit feature. Ensure you configure the auto scale mode, I would just say. It also provides low latency index queries for fast retrieval of data. Choose the right partition key upfront and ensure you have evenly data distributed across multiple logical partition. Auto tune indexes for low latency queries. Configure change feed to identify anomalies quickly and also to move old data to the archival storage. We've seen that in demo. And we should TTL for storing only the hot data for an year and move the older data to the cheapest storage option like Azure Data Lake Gen 2. Uh, that will just help to optimize the cost. Yeah. So in nutshell, hot store enables low latency index query over your recent telemetry, and the cold storage will enables you commodity storage, and you can do the batch processing and basically long range queries on the cold store. This is all about this session. Thank you all, and you can find me here on the LinkedIn and Twitter.